Welcome to a 3x3 example with complex eigenvalues. So again, recall, if we have the system y prime is equal to ay, where A is an n by n constant matrix. If we have lambda equals alpha plus beta times I is an eigenvalue with eigenvector psi is equal to u plus iv, then we get y1, which is u times cosine of beta t minus v times sine of beta t, all multiplying e to the alpha t, and y2 equaling v cosine of beta t plus u sine of beta t e to the alpha t are both linearly independent solutions. My screen's not updating. Give me a moment. And trying again in this format. Again, we have y1 as u cosine of beta t minus v sine of beta t, all multiplying e to the alpha t. And y2 is v cosine of beta t plus u sine of beta t, all multiplying e to the alpha t. And these are linearly independent solutions. So let's now go ahead and take a look at the example. Y prime is equal to the 3x3 matrix A times Y, where A is first row 2, 0, 0, second row 1, -1, -5, and last row 1, 2, -3. And our job is to find the general solution. So the first thing we should do is find the eigenvalues. So we are looking at the determinant of 2 minus lambda, 0, 0 for the first row, 1, -1 minus lambda, -5 for the second row, and 1, 2, -3 minus lambda for the last row. This determinant should be equal to 0. Again, our first row has only one non-zero entry. So this determinant is simply 2 minus lambda times the subdeterminant -1 minus lambda, -5, and then 2, -3 minus lambda for our second row. The other two entries in that first row were 0, so we would just have a -0 times the subdeterminant and a +0 times the subdeterminant equaling 0. So this gives us 2 minus lambda times in brackets -1 minus lambda times -3 minus lambda, and then minus -10. All of this is equal to 0. That brackets becomes lambda squared. Then we have a +3 lambda plus lambda, so +4 lambda. Then we have +3 and +10 becomes +13. So we have 2 minus lambda times lambda squared plus 4 lambda plus 13 is equal to 0. We can complete the square on the brackets. That becomes lambda plus 2 quantity squared. That gives us lambda squared plus 4 lambda plus 4. We need another +9 to reach 13, or +3 squared. So we have 2 minus lambda times in brackets lambda plus 2, quantity squared, plus 3 squared equals 0. So this gives us, we could take lambda 1 to be 2, lambda 2 to be negative 2 plus 3i, and lambda 3 to be negative 2 minus 3i. So here are eigenvalues. Step 2 is to find the eigenvectors. So using lambda 1 equals 2, we are looking at 2 minus lambda, so 2 minus 2, and then 0, 0 for our first row. For our second row, we had 1, negative 1 minus lambda, and negative 5. So we are looking at 1, negative 1 minus 2, and negative 5. For the last row, we had 1, 2, and then negative 3 minus lambda. So we have 1, 2, and then negative 3 minus 2. This matrix multiplied by some unknown psi should be equal to 0. So this becomes the augmented matrix 0, 0, 0 with augmentation 0 for our first row. 1, negative 3, negative 5 with augmentation 0 for our second row. And 1, 2, negative 5 with augmentation 0 for our last row. If we leave the first and second row alone, so we have 0, 0, 0, 0, and 1, negative 3, negative 5, 0 for our first two rows. And then if we do row 3 minus row 2, 1 minus 1 is 0 for our first position. 2 minus negative 3 is 5, and negative 5 minus negative 5 is 0, and 0 minus 0 is 0. So we just have 0, 5, 0, 0 for our final row. This tells us that psi2 is equal to 0. We know that psi1 is equal to 3 times psi2 plus 5 times psi3. Plugging in that psi2 equals 0, we get that psi1 is simply 5 times psi3. So we can go ahead and pick our psi3 to be 1. And that means that psi1 would have to be 5. So we get the vector psi1 corresponding to our eigenvalue lambda 1 is 5, 0, 1. Now let's go ahead and work with one of our complex eigenvalues. We do not need to deal with both. So let's work with lambda 2, which was negative 2 plus 3i. So once again, we consider our matrix. We are looking at 2 minus lambda. So 2 minus, in parentheses, negative 2 plus 3i. And then 0, 0 for our first row. For our second row, we had 1. And then negative 1 minus lambda and negative 5. So our second position is negative 1 minus, in parentheses, negative 2 plus 3i. And then negative 5. And then for our last row, we had 1, 2, and negative 3 minus lambda. So we are looking at 1, 2, and negative 3 minus, in parentheses, negative 2 plus 3i. This whole matrix is multiplying psi to get 0. So forming our augmented matrix, our first row is 4 minus 3i, then 0, 0, and augmentation 0. Our second row will be 1, 1 minus 3i, negative 5 with augmentation 0. And our last row will be 1, 2, and -1 minus 3i with augmentation 0. If we do row 1 divided by 4 minus 3i, that first row just becomes 1, 0, 0 with augmentation 0. And then if we do row 2 minus row 1 over 4 minus 3i, all we're doing is canceling out that 1 in the first position. So we have 0, 1 minus 3i, -5, 0. And then similarly, let's do row 3 minus row 1 over 4 minus 3i. We again get 0 and then 2, -1 minus 3i. That's a very sloppy 3i. -1 minus 3i and then 0. As we saw in the 2 by 2 case, it's not necessarily obvious that the second row and third row are scalar multiples of each other. So let's just check. So our first row, we have 1, 0, 0, 0. For our second row, we are now going to do row 2 divided by 1 minus 3i. So we'll have 0 and 1 for the first two positions. -5 divided by 1 minus 3i. We can go ahead and multiply the top and bottom by the complex conjugate, 1 plus 3i. So this becomes -5 times 1 plus 3i up top. And down below, we have 1 squared minus 3i squared, which becomes 1 plus 9 or 10. And so we're looking at -1 minus 3i all over 2. So our second row is 0, 1, -1 minus 3i all over 2, and then 0. And as you can see, if we just did row 3 minus this row 2 over 1 minus 3i, sorry, minus 2 of these. So if we do row 3 minus 2 copies of row 2 over 1 minus 3i, they do just precisely cancel each other out, and we have 0, 0, 0, 0 for our last row. So we do get a free variable, which is good. We know that xi1 has to be 0 based off that first row. And then we know xi2 should be equal to 1 plus 3i over 2 times xi3. If we pick xi3 to be 2, then that means that our xi2 would have to be 1 plus 3i. So putting this all together, we have our xi2 vector is equal to 0, 1 plus 3i, 2. Again, if we rewrote this, we could also write this as xi2 is equal to 0, 1, 2 is the real component plus I times the imaginary component, which would be 0, 3, 0, since only that second row has an imaginary component. So the 0, 1, 2 is acting as our u. 0, 3, 0 is acting as our v. Our next step is to find our fundamental set of solutions. find a fundamental set of solutions. So we know our y1 is psi1 times e to the 2t. So our psi1 was 501. So we have 501 times e to the 2t. Our y2 and y3 will be based off u and v and our alpha plus beta I. So y2, we will have u times cosine of beta t minus v times sine of beta t, all multiplying e to the e to the alpha t. We had lambda was equal to -2 plus 3i. So we have our alpha is -2 and beta is 3. U and v we just quoted previously. So u is 0, 1, 2. So we have the vector 0, 1, 2 times cosine of 3t minus v. The vector v was 0, 3, 0. So minus 0, 3, 0 times sine of 3t. And then all of this multiplying e to the -2t. We can also write this simply as 0, then cosine of 3t minus 3 sine of 3t for our second position, and 2 cosine of 3t for the last position, all times e to the -2t. For y3, we have v times cosine of beta t plus u times sine of beta t, all multiplying e to the alpha t. Our v again was 0, 3, 0, multiplying cosine of 3t, plus our u was 0, 1, 2, all multiplying sine of 3t, and then this whole thing is being multiplied by e to the -2t. So we can rewrite this as y3 is equal to 0 for the first position, 3 cosine of 3t plus sine of 3t for our second position, and then 2 sine of 3t for the last position, all multiplying e to the -2t. So our final step is the general solution. So we have y is equal to c1 times 501 times e to the 2t plus c2 times 0 cosine of 3t minus 3 sine of 3t, and then 2 cosine 3t. All multiplying e to the -2t, and then plus c3 times 0, and then 3 cosine of 3t plus sine of 3t, and then 2 sine of 3t for the last entry. That vector multiplying e to the -2t. So this is how we can go about solving a 3x3 system with complex eigenvalues. Just a quick note. We now have the ability or the techniques to solve all 2x2 and 3x3 systems. Of the form y prime is equal to a times y, where a is a constant matrix. We have not hit all possible cases for repeated eigenvalues for a higher n, nor have we hit all possible cases for repeated complex eigenvalues. So for n larger than 3, we have not dealt with all possible cases of repeated eigenvalues. And this time around, for n greater than 3, we also have to include repeated complex eigenvalues. So we can somewhat generalize off the techniques we had used to develop, or of the techniques that we already built. I am not going to go through these higher situations. So we will not cover the remaining cases in this class. But as I mentioned, we do have the ability to solve all 2x2 and 3x3 systems, and we can solve many higher dimensional systems, or 4x4, 5x5, etc. We can solve systems for larger n as long as we don't have repeated complex eigenvalues, or we don't have repeated real eigenvalues with high multiplicity.